My name is Takahiro Morishita from Caltech IPAC. So today, I'd like to contribute to this wonderful conference by, introducing our database program and our discovery that I've been working with Massimo Schiavelli over there, and also glass ERS collaboration and ongoing database beacon program. I was actually a postdoc of Massimo. I was hired back in 2017, and I was promised that the data will be coming in the next year, but it didn't happen. And many things have changed. I grew a little bit old. I had a son, and I moved to Pasadena, and then now I'm working for Roman. But I haven't sold my soul completely yet, and I'm very excited to be here to kind of introduce our discoveries that we are making here. Anyway, let's get started. Sandro made a very nice introduction about early universe, so I don't have to repeat everything, but just to put some extra emphasis and some spice up. So we are looking at now, this dark ages cosmic dawn to epoch reionization, which I'm going to focus on in this talk. So the star galaxies, first stars galaxies, and AGN potentially, they are turning the state of the universe, changing the neutral hydrogen into the ionized state. And the picture image that that they have to ionize surrounding ionizing bubble. So we need ionizing photon from galaxies. And the question that I have to make here is why luminous galaxies, not the general galaxy population, but luminous galaxies are still interesting. The general consensus now is that the faint galaxies, they are the main driver of reionization. But I would still argue that luminous galaxies are unique, and we can learn many things about the universe, about the galaxy itself. For example, the luminous galaxy, the chance is much higher that we see large ionizing bubble, where we can see the Lima alpha photons escaping from the system. Also, because it's in the center of the kind of baryonic structure. So luminous galaxies are kind of signpost of where galaxy evolution might be advanced a little bit compared to the field galaxies. So in many senses, luminous galaxies are still interesting targets. And especially in this talk, I will focus on two kind of unique systems that were known from the time of pre-JWST. And my ultimate goal here is to not to just highlight what we are discovering, but because we are now very important phase that we have passed the discovery phase of JWST from cycle 1. And now we are switching to the understanding phase, what is going on, what is in general going on to the universe and galaxies. So hopefully my talk can lead to that part by kind of raise questions and maybe some issues that we are confronting. So anyway, I will start with this very interesting object kind of system at redshift 7.9. This is a part of the GLASS collaboration that I've been part of. GLASS, as many of you may know, is one of the early programs that was executed and then made public. So many people also made use of the data. And here I just like to highlight our discovery of this very interesting 7 galaxies. So there are 7 galaxies that were identified by HST, but back in them, we didn't have spectroscopy. So we put MSS slit on many high-resolution galaxy candidates, and among them, 7 we confirmed with near-spec MSA, and we detected oxygen 3 5007 line, and also H beta line in some cases. And the surprise was that the 7 galaxies, they located at exact same redshift, 7.9. And if you can see on the left side, they are located very close together. So given the proximity, they are located within 60 kiloparsec here. It is making a very extreme overdensity, which we don't see many often. And another surprise that we found was, none of them shows Lima alpha emission line. All 7 were detected in oxygen 3, but none has Lima alpha, which is kind of different picture that we have seen in the previous slide, that overdensity or luminous galaxies are a good place where we expect to see Lima alpha photons, but we didn't. So we investigated why is the case. And actually the answer is not that difficult. First of all, IgM neutral fraction is high back in time. The beauty of the derivation is that not only we can detect oxygen 3 lines and confirm redshift, but we can use that redshift as a systemic redshift. So we can go back to the wavelengths of Lima alpha, exact wavelengths. So we can check the limit, and the absence is a measurement. So we can get inference on the neutral fraction. Here, we have 7 galaxies at the same redshift. So we have very strong constraint on the neutral fraction from them. I would like to add another kind of possibility on top of the IgM. ISM may also play that we don't see Lima alpha photons. As you see here on the right top, 5 of 7 galaxies are actually interacting and merging, and that's where we expect enhancement of dust. So, and on the left panel, I show the UV spectral slope, the redder slope on top and the bluer slope on the bottom. And 7 galaxies are they located above a main sequence of the UV slope. So they are actually redder compared to the other reference samples at the same redshift. So my conclusion from here is that overdensity may not provide necessary Lima alpha photons, but we can still see galaxy evolution might be accelerated there, a little bit enhanced. And I'm switching the gear to another object that I've been working with Massimo. So there's a JD1 galaxy that was very famous from the time of HST. That's originally detected by ALIMA oxygen 388 micron. That was a redshift record holder for a while. Another unique nature of this JD1 is it has strong 3.6 to 4.5 micron excess that indicates the presence of all stars in the galaxy, in this galaxy at 9.1, which is very unique and very interesting. So we took near-com image first. Here I'm showing HST and also Spitzer, 2 images. You can see Spitzer detection is 9 pixels, but still we can see the blob there. Now turning into near-com, you can see how wonderful the near-com is. And the first thing we noticed was that JD1 has triple cores in the high resolution images. So it turned out that database might be merging or it might host star-forming clumps in it. So we have the same wavelength coverage as Spitzer, but we didn't find a significant break. So the claim turned out to be kind of much weaker break. That means that JD1 is rather a young star-forming galaxy that we might be seeing somewhere else as well. The stellar mass turned out to be slightly less than what was claimed originally. Still, interesting nature can be revealed by the spectra. We took very deep spectra of this galaxy at redshift 9.1, and we could detect auroral oxygen 3 lines, which is very sensitive to the temperature of ISM. So we can measure the temperature that leads us to the direct measurement of the oxygen abundance. That is very cool. And then here, I'm showing that I'm still saying that JD1 is unique in chemical enrichment. So JD1 is located above the main mean relation in mass, stellar mass versus metallicity relation here at the same redshift. So it's enriched in oxygen. And then if I plot other high redshift galaxies from JWST, from our program and also other public JAYS program and other public programs, JD1 is located above, than other galaxies. And here, we focus on the global properties of these high-redshift galaxies. The first thing that is that on the right side, the metallicity, mass-metallicity relation evolves from the local relation, something that we already know. But another thing that we noticed with this larger sample than the previous one, was that we see larger scatters than that we expected originally. So we tried to reduce the scatter by adding the redshift or star formation rate, but it didn't help. So we couldn't resolve the larger scatter that we are seeing. So we are now trying to understand what is causing large scatters. The first is astrophysical. Of course, galaxies at high redshift, they are very intense. They are small in size, and they are high star forming. And then the potential might be much shallower compared to the nearby or low redshift galaxies. And of course, the accretion rate is much higher. So on the left panel, I'm showing that the surface star formation rate density. So they are very compact and the star formation rate is high. So basically, early galaxies that we are seeing is that in the star forming regimen, starburst, and maybe in some case, U-log of the local universe. So that's one remark. And another potential interpretation is not astrophysical, but systematic. So we have to be aware of this. On the left, I'm showing the deviation from the determined relation as a function of the flux loss by MSA. So we are putting very small shadows on galaxies. And in many cases, high redshift galaxies, they should be okay because they are like P-like and very compact. But galaxies like JD1 and also galaxies behind massive clusters, they are extended. So we might be losing some fraction, maybe large fraction of light out of the galaxies. And by design, it is placed, MSA shadow is placed on the center. So it indicates that we might be overestimating the global metallicity of galaxies. So if JD1 has a strong metallicity gradient, that might lower the global metallicity estimate in the end. So in my last minute, I'd like to kind of introduce ongoing program, and the question that I have here in mind is, the cycle one result represent the entire universe? Here I'm showing the cosmic structure, and then the Newcomb point of view is very small compared to the large cosmic structure. Even though there are many very large field of view surveys ongoing, still they are not large enough to capture the entire universe. And we have to have some supplemental surveys that can be done pure parallel surveys that we are now working on. By looking at the random pointings of the universe, then we increase the statistics, we increase the sampling of the universe. And our program will provide large enough volume that we can discriminate different models by counting the number of the galaxies detected in the Newcomb data. And here, I'm just making my point that we have actually 090 filter, which in some case underused in some extragalactic surveys, but this is very critical to get reionizing galaxies, because otherwise we would have to miss redshift 8, redshift 9 galaxies and completely zero. So we are making our effort to make data public to the community at the end of the survey. And here, just emphasize my point on JD1, on the overdensity that I introduced first, is a unique laboratory that we can see the connection to the cosmic, the universe, and also galaxy evolution itself. JD1 turned out to be a young star-forming galaxy, but we now have a good metallicity measurement. Then we are seeing some large scatters, but we have to be aware of systematics of MSA as well. And lastly, I briefly introduce our ongoing surveys. So I stop here, and I'm happy to take questions. Thank you very much.